Let's welcome Dr. Barry Barish.
It's a great pleasure for me to join this summit as a scientist. I'm going to follow the same theme that we've heard, starting with Peter, who told us that we live in a great time, and I'm going to agree with that as a scientist. He also told us that we live in a time where we can solve incredible problems and do great things. And we heard about two fantastic abilities to explore in the last two talks: deep underwater and in space. I'm going to talk about the ability to discover, mankind's ability to discover by doing science, and I'm going to talk about physics, which is my subject. Before I talk about that, since this is a crowd that's interested in applications, let me say that although everything I talk about and my own reason to do this is very much knowledge, learning about how the world works, which I think should be the goal of modern mankind. The kind of science that we do impacts our ability to do the kind of things that are done by entrepreneurs maybe a few years later. Just as an example, I'm going to talk about Albert Einstein. I'm going to talk about his theory of general relativity, one of the most abstract theories introduced in 1915 that physicists didn't understand very well for quite a while. I'll talk about it in terms of something called gravitational waves, but just to let you know that learning this knowledge was essential for us to make GPS work. So all of you use GPS, but you wouldn't stay on the road more than a couple minutes without the GPS correction that's made in the satellites due to general relativity. A second example, close to me, is in the laboratories next to me not so long ago. They were working on something called nuclear magnetic resonance. That was totally, again, a physics understanding of a physics problem. And that's now turned into, they dropped the word nuclear for maybe obvious reasons, but it's a magnetic resonance imaging that we use and is a big part of medicine. A third one is what I do, which is we have a project called LIGO, which I'm going to show you. The L on the beginning of it means laser. And it again came from a fundamental physics experiment, spontaneous emission, done about 50 years ago. Spontaneous emission was the physics term which lased and made a laser, which it took more than a decade before anybody thought there might be applications. Now it's a multi-billion-dollar industry. That's the last I'll talk about applications. I'm going to talk about physics. This is a fantastic time to do physics, as it's a fantastic time to do exploration or to try to solve the world's problems. It's a fantastic time because we have the ability to do it because of technology. We have governments that are willing to support us to do research. And we do these things typically internationally and in large teams and efforts. And so I'm going to start by talking about just what's been done already in the same spirit in this new century. The first thing, near the year 2000, that was done and was was awarded in this last year's Nobel Prize, was the discovery that an elementary particle that we talk about, the neutrino, has mass. The neutrino was discovered or proposed in the 1930s by Enrico Fermi, clever enough to make up the word neutrino, neutrino meaning neutral one, and in Italian, INO at the end means little neutral one. So little neutral one didn't tell us whether the mass was zero or whether the mass was tiny. And in the last decade or so, we've been able to show in a large international experiments done in Japan and in Canada that the neutrino has mass. There's 3 different neutrinos. So the next question is, what is their mass and how is it related to each other? And there's a very important experiment being done here in China, in Daya Bay, which is addressing exactly that question. So one physics discovery leads to the next important question, which, as I say, here is being looked at in Daya Bay. The second discovery of this new century was done, and people have heard about this, the so-called Higgs particle. This is fantastically important in our understanding of elementary particles, the things that make us up. We have a theory, and have had theory that we've refined for years. It's actually a model that we've refined for years that describes the particles that we have that we call elementary particles if we make them in large accelerators. But that theory was completely happy having particles that have no mass. But particles do have mass, and we have mass, and the Earth has mass. So where mass comes from is something that somebody had to add. The theory for that was developed by Peter Higgs and a couple others 60 years ago, 50 years ago. And it was discovered at CERN, the big laboratory with a particle accelerator in Geneva, Switzerland, 5 years ago. The graph that shows the little bump is the Higgs itself, but the more impressive one is the one that shows on log scales the fact that the coupling of this particle is dependent on the mass, linearly dependent on the mass of the particles it couples to. Those are all the so-called quarks that we have, and over a factor of 100, it couples to mass. All the other particles that we have couple to electromagnetism, or weak forces, or strong forces, and not directly to how heavy something is it actually interacts with. So this is the underlying theory and idea then, and particle that creates mass, a very important problem, and now one that we can grapple with. I'm going to talk about the third great discovery, maybe the most important, of this new century. And that's what we call gravitational waves. We've observed black holes, I'll describe what that means, and colliding and creating gravitational waves, which we have detected and are shown in a familiar plot now, which shows a wiggle that gets narrower and bigger in 2 different detectors 3,000 kilometers apart. They're called LIGO. LIGO is shown in the big picture here, and I'll talk about it a little bit more. So this picture here is not an animation. It's not a rendition of, it's a rendition of the actual data that we took that discovered gravitational waves using general relativity to model what the shape looks like in the curves that I showed you before. And the picture has 2 black dots that you see. Those 2 dots are black holes. What is a black hole? A black hole, these black holes, are called stellar black holes, come about when a big star collapses into a small enough space with all its mass so that the gravity is strong enough so that nothing can get out. And that creates a place in space that's basically a black hole. So these are 2 black holes. The next thing to realize is that each one of them is smaller than the size of Beijing. Yet each one of them weighs 30 times the mass of our sun. So that's how much mass is packed into something the size of Beijing. They're separated from each other in this picture by less than the distance from Beijing to Shanghai. They're going to go around each other. They orbit each other just like the sun, the Earth around the sun, or the moon around the Earth. Each time they orbit, now they're orbiting, this is using our data. Each time they go around, there's acceleration involved. By Einstein's theory of general relativity, it radiates away energy. That energy goes away in the form of what we call gravitational waves. And this merges into one single object. And when it merges, which is now in this picture, it rings then a little bit. So when we look again at that picture, I'll describe it to you in terms of this visualization that you just had. So this again is a little movie of the two objects merging. And as they merge, they emit, because of the acceleration, gravitational energy. In the case of the signal that I saw, the amount of energy was about 3 times the total energy in the sun. Now that's a gravitational wave going out through the universe, eventually coming to the Earth. And the phenomena that happens is, which has to do with general relativity, is that it slightly distorts space and time as it passes by. So in this picture, it's slightly changing the shape of the Earth, squashing and stretching it, stretching and squashing. And that's the phenomena we use to measure it. We can't use the whole Earth, so we use a detector that's shown in this picture, and that's LIGO, which I'll describe to you a little bit so you can see what's involved in making this measurement. This is what we observed. So what happens is that when the objects are fairly far apart, they're at low frequency, that's on the left of the plot. As they come together, they go more rapidly, and eventually they merge, and then they ring down a little bit at the very end. These two traces, which look essentially identical, are taken in 2 different instruments, 3,000 kilometers apart, and the little line that's drawn through it is Einstein's theory of general relativity. This is the main picture of Einstein's equation of general relativity. It basically is totally different than Newton's theory. Space and time are unified into a 4-dimensional space-time, one word. Although Microsoft doesn't understand that yet, it still puts a little wave underneath it. And that theory then warps space around an object. So here's the Earth and the sun has then warped space around it, and that's what holds the Earth around the sun. Einstein then, 1 year after he developed and published the theory of general relativity, recognized that the equations had similarities to electrodynamics. And in electrodynamics, we have electricity, we have magnetism, but we also have electromagnetic waves, light waves, infrared, ultraviolet, X-rays. So he then proposed that there would also be in gravity gravitational waves. And this is the paper he wrote in 1916. He rewrote another paper 2 years later, which developed the fact that the source of gravitational waves comes from a so-called quadrupole moment. You might recall that in electricity, if I take 2 charges and I oscillate them, I make an electromagnetic wave. Hertz discovered that he could do that and detected it in another room. We can't do that, this is too weak, so we have to go into space and find something that's very violent, like the collision of black holes. So if we look at that collision of black holes, I show it here. The masses are 30 times the mass of the sun. They're about 100 kilometers in size. The frequencies that we detect them at are about 100 hertz, and they're about 1 billion light years away. The strength of the interaction, which is the equation below, is proportional to the length, to a length change in stretching and squashing space, and it's 1 part in 10 to the 21. That's the experimental challenge that we've had for decades. How can we measure something as small as 10 to the minus 21? So let me remind you how small that is. Everyone knows what a meter stick is. If I look at a human hair, it's 10,000 times smaller than a meter. If I look a factor of 100 smaller than that, that's the wavelength of light. That's about a micron. If I go 10,000 times smaller than that, I am at the size of an atomic diameter, an atom. That's 10 to the minus 10 meters. If I go 100,000 times smaller than that, I'm the size of a proton, which is what we use in these big colliders. And then I have to go 1,000 times smaller to get to the sensitivity that we detect in LIGO. So we're going to detect the fact that there's a change of distance between the vertical and the horizontal in this picture here of 1 part in 10 to the 21. We do it by what's called interferometry. Interferometry takes the laser beam, which is on the left, splits it into a beam that goes vertically and a beam that goes horizontally, compares how long it takes to go down the two arms. If they're equal length, it comes back at the same time. One cancels the other, and there's no effect. But if one arm gets a little longer and the other one a little shorter, they get out of phase with each other, and that's what we measure. The way we can get down to such an incredibly small number is by making the measurement many, 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 many times. That means by having lots of photons to do the measurement. So this is just a schematic picture of what we do. We basically start from the laser, split the light in the two directions, send it into these two long arms. They're kilometers long, and trap the light so it bounces back and forth in those arms, and then look for them to have a difference in the two that we detect in a photodetector. We have two of the apparatus so that we can tell that what we see is real. That's separated by 3,000 kilometers. One in the state of Louisiana, and the other one in the state of Washington. This is the apparatus itself. This is in the state of Washington. The long pipe is because we have to be in high vacuum. This is the biggest vacuum system in the world. It's 16 kilometers of vacuum, 1.2 meters in diameter, and it runs at almost 10 to the minus 9 torr. This is just our control room, and that's kind of what it looks like. So the apparatus itself, the laser that we use is rather special. We had to develop it. It's a kind of laser that's used commercially, neodymium YAG laser, but it's one single line and it's stabilized by factors of thousands better than a commercial laser and more powerful in a single line. 200 watts, neodymium YAG, and basically stabilized in power, in frequency, and in pointing well enough to have this very stable beam. This is the trick and the technology that took us 22 years to develop that enabled us to measure this event that I showed you. And that is a suspension system that allows us to have the mirrors that are on the end, which is we call test masses, completely free to move by gravitational waves, but yet isolated from the Earth's movement. We do that by a combination of passive isolation, which is like the shock absorbers in your car, 4 layers of them, and active seismic isolation, which is like you use in earphones on an airplane to cancel ambient noise, only we have to do it in all the dimensions. This is developed to be much better, of course, than others, and that allowed us to improve our resolution. So what's shown in this graph is the place where we're able to look for gravitational waves. The sensitivity where you can work experimentally on the Earth's surface is the same place where the ears work. Not that we do audio work, but it's where the Earth is quiet. If you go to lower frequencies than our ears respond to, the Earth is really shaking and noisy. Therefore, we can't work at very low frequencies either. At the highest frequencies, the reason your ears cut off is because you have to sample too quickly. And again, in our case, if we go to high enough frequencies, the number of photons is less and less as we sample more quickly. So this is the shape of what we see. The curve on the top was the original curve we had before we put in new technologies. And the improvement at low frequencies is a factor of 100. And that we had 1 year ago when we made this discovery. That discovery we announced in February. We actually have 2 more samples of events. They're all shown here. On top of the sensitivity curve, there's 3 bands. You have to imagine each of those comes in time over a period of seconds. And how tall it is basically its strength. And how far it goes out is what frequency it goes to. The first one that we saw is the top one. It's biggest, and it cuts off at the lowest frequency, and that's because it was very heavy. The 2 masses were, when it combined together to make a final black hole, was over 60 solar masses. It's shown also in the wiggles in the top graph on the right, and the other 2 are in between. But all of these are heavier than any black holes that were suspected by any astrophysical arguments. This picture here is the general relativistic interpretation of what we've seen. So on the top, you see one black hole going around another, getting closer, merging, and then making one object. On the bottom, which is more important, if you look at the right-hand curve, it's the separation between the 2 black holes in units of 100 kilometers. So they start 400 kilometers apart and end up merging together less than 100 kilometers. More impressive is the graph on the left and the one rising, and that's the velocity. When we start observing it, these 2 objects are going at about 1/3 the velocity of light around each other. So we have 2 objects, 30 times the mass of the sun, between here and Shanghai, going around each other at half the speed of light by the time they merge together. Hard to imagine. That's our observation. We'll do a lot more in the coming years. We're improving this detector. You'll hear more about future measurements here on Earth. But before I end, I want to point out that this opens up a whole new way to do astronomy. Just like astronomy's done in all kinds of different devices for electromagnetic astronomy, infrared, ultraviolet, in space, on the ground, here we can do the same. Phenomena that take milliseconds, like the ones that I just showed, are done in objects like LIGO, which will do much more as we project in the future. The next thing that'll happen is an experiment in space. It's called LISA. It involves 3 satellites separated by long distances, and they will measure at lower frequencies. Yet lower frequencies can be measured by timing pulsar signals over some period of time very accurately that we measure here on Earth. And lastly, we can measure back to the very early stages of the Big Bang, the earliest times, because gravitational waves are not absorbed like light waves or photons, and so that'll be done. In parallel, we'll develop the next set of colliders, as I showed at the beginning, and we expect that we'll be able to then understand the phenomenon of the Higgs particle. As I said, a phenomenon of understanding what the real theory is. We use the word standard model because we don't have a theory. And the ambition is here in China to maybe build this device in China. And so the proposal that's being developed is to build this device in China. And I think those of us who do this science in the world are very hopeful that maybe that'll happen. That's it. Thank you very much.